We only use 4 for
So you get, I think it's 2 gigs.
So this is as good time as any to get started again. Thank you for being here. What are we doing today? We're going to finish the single cycle control, do a modification to it, show you how we can introduce a new instruction, and then if we have time, we're going to start talking about the other type of implementation. Just to remind you, what we did yesterday, we talked about the data path, and we also talked about the control. And I want to finish the control. The data path is a combinatorial circuit that contains edge-triggered registers that will change on the next rising edge. The whole point is that by within one clock cycle, you're going to read a new instruction from the instruction memory, allow sufficient time for all the signals here to stabilize, so by the time the next clock cycle arrives, the rising edge, you have the right values to be loaded to the storage elements you're going to change. The PC always changes, and depending on the instruction, you may change the register file or the data memory. And the flags. These are the only things that are visible to the programmer. Registers, memory, PC, 0 negative flags. That's it. Okay? So the data path is capable of performing all the operations necessary by any instruction at any given point in time. It just cannot decide what to do. So the control is a piece of circuit that goes on the top. It looks at the instruction and the 0 negative flags and decides how to set all the control signals, which are underscored here, to perform the action necessary for that particular instruction. We said when a clock cycle begins, these wires have leftover values from the previous instruction. This is okay because nothing is changing. The change is going to happen on the next rising edge. We got to wait long enough for these values to stabilize to the new values for this instruction, for the control to look at those, to set the right control signals, and then for the circuit to do the right thing. You just make your clock cycle long enough. That's the idea behind this implementation style. So we've done a lot of stuff. Let's look now at one other instruction, which is the OR-I. OR-I, I want to remind you what it does. It has the lower 3 bits of the opcode being 1111. Down here you can see that. It doesn't care for the 4th bit, because that's part of an immediate 5. The upper 5 bits of that opcode, the 8 bits you get from memory, form a constant. So we're going to look at OR-I, and then OR-I implicitly changes K1. It's not part of the instruction opcode. You know from the manual it has to change OR-1. So let's see what we got to do. So when the control eventually sees a value on these wires whose lower 3 bits are 1, 1, it realizes that this is an OR-I, and then it has to set the control signals accordingly. Okay. So let's see. PC select. What should it be? PC select is the signal that decides whether on the next rising edge the PC is going to be changed to PC plus 1 or PC plus 1 plus some offset. This is not a branch, so it should be PC plus 1. So it should be this path here. So it's 0. For that reason, that thing is going to be 0. And there we go again. Okay, so that's going to be 0 here. PC write. So we change the PC, of course we are. Every instruction is going to change the PC. And just heads up, PC write is always going to be 1. So it's really not a very useful control signal. You always change the PC, period. Okay. Now, do we write to the register file? Of course we write to the register file because this is an OR-I. We do. Now, do we read from memory? No. Can we? Of course you could. So you could put X. However, let's pretend that memory is expensive. For that reason, I'm going to make that 0. I'm not going to read from memory. What should be the value you're going to write to the register file? And what I mean by that, where should it come from? Should it come R1 select? Sorry. R1 select is what is the register name we're going to give to the register file as the name of the register to read as part of the first read port, the one on the top here, register 1. Will give you some data, and the name of the register we're going to write. So it controls that multiplexer over here. Should it come from the upper 2 bits of the instruction, or should we force 1 for K1? Again, just to move forward, this is OR-I. We have to force explicitly K1 because that's what the definition is. So this value here has to be 1 according to that diagram. Okay. All right then. Are we going to write to memory? Absolutely not. What are we going to calculate in the ALU? I don't remember what the value is. I will guess it's probably add, subtract, NAND, SIFT. I don't remember. So it's
That's ALU2's.
oh, LU2 is the input, right? What should be the second? You're right. Absolutely. I'm lost again. What should be the input to the second port of the ALU? Should it be the register file? Should be the immediate 5 0 extended to 8 bits, or should be the immediate 3 0 extended to whatever 8 bits? This is OR I. The second operand is the immediate 5. For that reason, ALU up should be 0 1. Sorry, LU2 should be 0 and 1. Okay. RFE now is what I was describing before, which is where is the name for the first register coming from. It doesn't come from the instruction, it comes directly from the machine itself, so that has to be, no, what am I talking about? I'm completely lost today. This is the value that goes into the register file here. So RF in down here is the register in on this diagram. Should it come from the memory or should it come from the ALU? So it should come from the ALU, 1. Sorry for confusing today, I gotta get my act together. I'm a bit distracted. So ALU up, I don't remember what's the encoding. We have to flip the slide. So let's write OR I, OR. And we just go and we'll, that's supposed to be an OR, by the way. So this has front collision. Anyway, so that's an OR. It is a 3-bit value, which is what we defined on the slides before. And finally, should we change the flags? Yes, because OR I changes the flags. And that's supposed to be a 1. You okay with this? You follow it? Is this a sign of desperation in your eyes? That's from a song. Anybody knows the song? No. Okay, good. Shift. I'm not going to do shifts. I don't like shifts. You can do that on your own. Let's do a branch, and we're done. So let's do branch, not 0. Notice now that before we were having both of those being X's because we couldn't care less what the condition codes were for those condition flags. Here, because this is looks at the 0 flag, we expanded into the 2 rows for that. Okay. So next question is the following. What should be PC select here? Well, it depends. This is not 0. That's the instruction. If the flag is 0, then we want the branch to be taken. So PC select should come from this guy, the taken address. So it should be 1. Here I should write 1. Why? Because this is non-zero. The 0 flag is not true. So the value was non-zero. So this should be 1. Otherwise it would be 0. That's the branch. Do we write to the PC? Of course we do. Do we write the register file? No. Do we read from memory? No. Do we care what's the name of the register we're going to read from the register file? No. No. Do we write to memory? Absolutely not. Do we care what's the second operand of the ALU? No. Do we care what's the value we're going to send the register file to write? That's a statement a lawyer will make. We're not going to write anybody, so no. Do we care what operation the LU will do? So 3 X's. Are we going to change the flags? Absolutely not. So notice anytime there is an element that's a storage element that's visible to the programmer, we got to set values there because it's whether we change them on that. And the only element that's visible to the programmer that changes from a branch is the PC. Everything else should be zeros. Okay. Everybody okay with this? Okay. I'm not going to do this. You can do this on your own. The only difference between this and the previous one is just the values for the PC select are the opposite. And very similar here. This is positive or 0, right? You have to look at what it means. Okay. At the end, again, this is supposed to be the full truth table of the thing. Don't look at it. Look at me. Okay, look at me. Okay, because I'm going to tell you something very important about this. This is supposed to be the truth table for the control. Okay. Again, this is the input variables. There are 6 of them, 6 bits, opcode, the 0 negative flags. Right? And then these are the control signals. This is supposed to be correct. I wrote this. Do I trust myself with my life? Not for this one. That is, if my life depended on this, I will go and double check it, triple check it, four check it, whatever, quadruple check it. Okay? So look at this. If you find any bugs, let me know. Right? So do not think that this is gospel and it's correct necessarily. It's meant to be correct. There's no intentional bugs here. If I were to bet whether there is a bug here or not, I will bet that it probably is. Okay? But as long as you understand the concept of how things are done, use this as an exercise. If at some point something looks off, it might be that the simplest answer is the right one. I made a mistake. Okay? So email me. That will be the quickest way to get an answer, if you wish. Okay? So don't spend too much time fretting over this. Doesn't make sense. If I didn't make a mistake, that's okay. So what? I mean, we're going to exchange an email. I'll tell you, oh, no, this is right, and this is why it's right. It's going to disappear in the ether a couple of days later. Nobody's going to remember about it. Okay? So far, so good? Okay. So last thing I want to do about the single cycle implementation is to say, let's make a change now. Let's say we build this machine, and now we want to build the second version of it. And for whatever reason, the second version is not going to be exactly compatible with the previous one. We're going to change it and add a more powerful instruction to it. So the idea here is we're going to change adds so that the second operand actually comes from memory as opposed to from a register. So the format here is supposed to mean use R2. So we're still going to read the instruction as far as the opcode is concerned looks identical as before. However, what it does, it has a different meaning now. We're going to read R2, but we're not going to use the value as an operand to the add. We're going to go to memory. Look at this. And then whatever we got from memory, we're going to add to R1. And the question is, can we support this with the machine we have? Or what changes do we need to make to support this? Okay? Now, long story short, you have to sit down and see what are the operations necessary. You're going to see that the machine is perfectly capable of taking R2 and going to memory and reading a value from it. However, what is not capable of doing it is taking the output of the memory and sending it to the LU to be added with another input. It's not capable of doing that. So the only change that's going to be required for this is, for my data path here, what I'm trying to say is, as you can see, there is a way to send the bits 5 and 4 from the opcode to go to the rest file, so we can use R2 from the opcode to read a value. That can travel as part of an address to become an address to memory. We can read a value from there using that as an address. That value, however, only flows as potentially an input to the right port. To do an add on top of that, we need to grab this value and feed it as another option to this multiplexer here, because that's the second operand. If we do that, we're done. So the only change that we need to do structurally to our data path is this. That's it. Okay? But you have to make that change, otherwise you cannot support that instruction. And then, of course, when we write the control, we got to go and change the control so you can do all these compound actions together. But you can do that. Long story short. Okay? Any questions about this? Alrighty then. Just side note here, when you build machines like that, simple machines like this, it turns out one of your most critical components is often enough the shifter, the thing that does shifts. And just as a side, well, let's relax a little bit. Let's talk about some side thing, and then we're going to go to the other implementation. Is I'm going to show you what's called a barrel shifter. You haven't seen that before. So a barrel shifter is a circuit that accepts an input of data plus a control signal that says by how many positions to shift that. So notice this is a simple either shift or don't shift by 1 bit position shifter. Look at this. This is an 8-bit input. This is an 8-bit output. And if you notice, if you follow the black lines, right, the direct lines, the flat ones, you can have every input go directly to the corresponding output, same index. In 5 can go through this path to out 5, and this applies to everybody. So this means don't shift. However, there's a control signal that controls all these multiplex. If you make that 1, what's happening here, notice that in 5 goes to becomes out 4. So we're shifting right. If you were to view this on a board, bit 5 to 0. Fair enough? So this is can support for 1. Now, here's the thing. We just built a circuit that can shift by either 0 by 1 bit positions, right? How about a circuit that can shift by 0 to up to 3 positions? Okay. So you're going to give me a control signal that's going to have 2 digits, an A1 and A0. So the possibilities here are the following. Don't shift, shift by 1, shift by 2, or shift by 3. And I want you to view this now as a 2-step process. This is either you shift by 1 or not. and this is you shift by 2 or not. Fair enough? So this leads you to this structure. And if you notice that, there is a first stage that is identical to the one before, either shifts by 1 or not. Notice the connections is from in5, you go to the guy upstairs immediately, 1 floor up. The second stage, however, the connections are 2 floors up. So if you view it like this is what it does. You can choose to first shift by 1 if you wish or not, and then whatever comes out, shift it by 2 or not. This circuit can do anything between 0 and 3. Fair enough? And you can keep going. It looks like a tree. I mean, that's what it looks. If I wanted to do by up to 8, yes?
On the bottom, there's a blue and orange arrow. They're not connected anywhere.
Yes, so it depends on whether you want to do shift arithmetic or not, right? It will come from somewhere, or if you want to do rotates. If you want to do rotates, you can treat this as a donut. Take the thing that's in the middle of a toilet paper, wrap this around it, right? So the 2 ends touch, so you can make it rotate if you want. That's choices. Okay. What I was about to say after this is that you can add 1 more layer if you wish, and now you can shift anywhere between 0 and 7. The next layer, the connections are going to be 4 apart. Keep going. Okay. This is one of the slowest things usually, for whatever reason. And at that point, my patience with drawing things stopped. So you're not going to see anything more than that. Fair enough? Any questions up to this point? Otherwise, we're going to go to multi-cycle, which actually is it's a bit more powerful implementation method, because it will allow you to, what did I close? It will allow you to implement any CPU. As I said, the single cycle has a limitation. You can implement any processor as long as it needs to access every structural element only once per cycle. The next implementation doesn't have that limitation. Okay, I'll take this as a no, and I move ahead to the multi-cycle one. Okay, now, what we did for the single cycle, I derived the whole thing. As I showed you in the beginning, there was nothing. Let me show you a logical way of deriving how this is done. I am not sure I can come up with a nice way of doing this for this way. So what I'm going to do is I'm going to tell you this is it. Now let's understand why it is like that. And I think out of this, it's going to grow on you, and you're going to be able to do the same over and over again. So what we're going to do now is the following. As the name suggests, this is an implementation that actually takes multiple cycles to execute every instruction. So it kind of more appropriately reflects the life of a CPU. Remember when I drew the CPU loop? I was drawing boxes and we're saying first you do this, then you do that, then you do that. So we're going to view every single step as a cycle here. Now, don't get carried away by the fact that this is a multi-cycle, right? Cycle is a unitless thing. It means nothing. What is a cycle? A cycle can be the cycle time of the fruit fly, which is a couple of hours, whatever. I have no idea, but it's not the same. It could be a cat, which is a 10, 15, 20 years top. So it could be a person, 80 years. So it can be anything, right? So even though this is going to take multiple cycles, at the end it's going to be faster because the cycles themselves are going to be much, much shorter. Okay? And another property of this is that it will not use the same number of cycles for every instruction. That's another benefit. Now, this is not the best way of building processors. This is a very powerful way. However, it will allow you to build everything and anything. And it was the way that people who were building processors up to some decade ago. However, mid-80s maybe. And it is a method that you use for low-end stuff. Okay. It's fairly credible. So, long story short, what I'm going to show you now is a circuit that can implement this thing. This is a table. If you notice, the table has a bunch of rows. There are labels on top. The rows correspond to different instructions. Some of them are grouped together because as far as the number of steps are concerned and what happens in those steps, they're almost identical. The things that change is, for example, what operation may happen in the ALU here. Okay. Now, rows are cycles. Notice this goes up to 5. Another thing that should draw your attention, or maybe another thing that I would like to draw your attention to, is that cycles 1 and 2 are identical. The first is fetch, the second is decode. You get an instruction, you say, okay, what does this thing tell me? This is the same for everybody because you have to look at the instruction to be able to differentiate. Right? After that, depending on the instruction, you may take up to 5 cycles. Remember the ORI? I told you ORI is going to be the one that's going to be causing problems for us. And it's going to be an interesting discussion what's going on over here. Right? And we're going to talk about something else that's nice in machines today, which is a much more powerful technique that we can use for many other things. Some instructions are going to take just 4 cycles. Fair enough? Okay. So let me go one by one to see what's going on. And we're first going to do the add. And before I show you the circuit, let's look at what this thing says. This is supposed to be a register transfer language. That's what people use the term. It's called RTL, affectionately. This is the acronym. If you look at every box, it has a left and right hand side. It's an assignment. What you have is you have some values you read, and then some storage elements you're changing. Some of those storage elements are visible to the programmer, like the program counter. Some of them are internal, and they're only visible to the implementation. This IR, for example, IR stands for instruction register. It's not something that the programmer can access. It's a register that exists in the implementation so that we can do this multi-step process. That's it. So it's not visible. You're not going to see that part of the program. It's there so the machine can work. Fair enough? Okay. So let's look at this. What is the first step? It says, go to the memory, use the PC as an address, and get some instruction and put it into some temporary register called IR. That's the first step. In parallel, update the PC and make it PC plus 1. Notice, why can we do this? Why can we do first step PC plus 1? What if this is a branch? Why is it okay to do PC equals PC plus 1? And that should answer the question why the people in Neos, when they have branches, no matter which direction the branch is going to go, there is a component that's common, which is PC plus 4. And in my instruction set over here, there's also a common component to branches. Whether it's fall through or taken, there's always PC plus 1. This is the reason why, because in the first clock cycle, you're sure that this is going to be useful. Whether the branch is taken or not, which by the way, you don't even know whether this is a branch or not yet, this is going to be useful. So that's why they made that decision, because it makes your life much easier at the implementation level. You can do this at the first cycle and be done with it. Fair enough? Do you have to do it here? No, you can do it at the very end as an extra cycle, but it's a nice thing to do early on because you want to finish things as quickly as possible. The more things you do in parallel, the less time is going to take you in total. Fair enough? Next thing, this is another powerful thing here. It's not going to be super obvious in the beginning, but let me point you this. What's happening here is the control is looking at IR. The control is looking at IR and is trying to decide what should be my next step. So we're going to assume it's going to take one cycle to decide how to set the control signals for cycle 3. Okay? There's some time that the control needs to look at those. Now, this could have been empty. We could have said, let's not do nothing. However, notice what we're doing over there. We're reading 2 registers. We're using the upper 2 bits of the register opcode, of the instruction opcode, and the next 2 bits to read what could be, that's the key operative word, could be R1 and R2. Will these always be R1, R2? Not necessarily so. They will be for these 3 instructions, add, subtract, and AND. R1 will be useful for shift, R2 will not be. None of them will be useful for RI, okay. For load, well, reading R1 is not necessarily, but reading R2 is useful. And for store, both of them are useful. And for these, they're useless. Okay. So what are we doing here? This is casino. You're saying, I don't know for a fact that what I'm going to be doing is going to be useful to you, but since I have a cycle to spare and I have nothing else to do, how about I proactively guess that this is going to be useful to you? So we're guessing that reading R1 and R2 using the opcode bits is going to be useful without having a guarantee that this is going to be so. There are 2 possible outcomes. Next clock cycle, we can decide whether what we've done was good or not good. Okay? If it was good, what we have done? We didn't wait 1 clock cycle to make sure we need to read these 2 registers. We read them earlier, and it turned out to be a good thing. It's like saying, let me do this just in case it's going to be useful. Let me look through the window just in case you're coming so I can come to the door and open it for you, rather than wait for you to knock. Right? It's going to save some time. Fair enough? If, however, you do not need this, what's the downside? The downside is you went to the register file, which was there, sitting idle. You asked it to give you 2 registers, so you bugged it. So maybe it was slipping, whatever, and you woke it up to give you 2 registers. But no harm was done other than expending energy to go to the register file. Because this is a machine, despite the fact that you use more energy, there's no side effect here. You read 2 values, well, you don't need them, too bad. It's not a bad thing. Right? It's a useless thing, but it's not a bad thing. So we're playing statistics here. Most of the time, what's going to be useful or not. This is a simple form of speculation. And this is the term that people use it. If you take 552, which is the computer architecture course, you're going to see that the machines that we use today, they do tons of this in many different ways for many different reasons. So your machine internally hedges its bets and starts doing things for you without asking you, just in case it's useful. And the reason this thing works well is that programs are not random objects. When they execute, they don't do random things. They tend to have specific phenomena that happen quite often. Right? For example, for data, there's a phenomenon called locality, which means what? If you access some particular piece of data, chances are you're going to access it again. That should make a little bit of sense. If you have a variable and you access it somewhere in your program, most of the time it should be intuitive that probably that is a piece of code that's going to use your variable a few times. Another phenomenon is that it's the same thing as life. Anybody, you invite somebody, the whole family comes in. Anytime you touch a particular piece of data, chances are you're going to touch the data next to it. Again, kind of makes sense. If it's an array, for example, you access a particular element, you're probably going to access the other one. If it's a variable on the stack, chances are you're going to access the other ones. I'll shut up because I think I'm putting you to sleep. Okay, good. Back to this. So this is speculation. We're ready to values. Let's go to the add. Next thing, now we're certain this is an add, subtract, whatever. If it's an add, we're going to go do the calculation of the ALU. We're going to take 1 clock cycle to do that. We're going to put the result into a temporary register called ALU out, not visible to the programmer. And at the last cycle, we're going to go write this back to the register file. Ta-da, done. PC was changed first clock cycle, that's okay. We don't have to spend an extra cycle. Why? Because we designed the instruction set so we can do that. Fair enough? Let's look at the data path now. Okay, let's try to familiarize ourselves with what we're looking at. Now, another nice benefit of this is that now we have only one memory. So data and instructions are properly in one piece of hardware. So this looks like the newest processor you have, at least from a programmer's perspective. So I have memory, which can be data or instructions. This is going to be used in the first clock cycle to fetch something. So I have my program counter as before, and I can go to it directly from the program counter, or I can do PC plus whatever for the branches. We'll see that. Second step, at the end of the first cycle, we're going to produce the IR, which is the instruction register. After that, we have the register file. This will look almost identical to what we had before. Right? It looks very similar to what we had before, if you can remember that. There is 2 registers in between here because in the second clock cycle, we're going to be reading the registers from here, and we stage them in these registers so we can use them on the third cycle. And there we're going to do either an ALU operation, or we may go and do a memory operation. If we get data from the ALU, it's going to go to this ALU out and then back to the register file. If we get data from memory, it's going to go to this memory data register and then back to memory. I'm going to explain that when we go instruction by instruction. So hopefully this gives you some idea of what's going on. Remember, we're going to do add now, and we're going to do cycle by cycle. Okay. First cycle. This is identical for everybody. We got to do the following. We got to send the PC to memory as an address. We're going to do a memory read, and we're going to write the result there. I hope you can see that there is a path for doing that. Let me try to draw the path. So we start from this guy. Got to activate this. And let's see if this works. So we go from here, there, right, to the address, memory read, and then we go through here, here. Can you see the yellow stuff, or is it visible? Okay, that's the path. That's the first cycle. Fair enough? Let's go to the second cycle. Second cycle, the controller is going to be looking at this, deciding what to do. In parallel, however, the data path is not going to sit idle. It's going to speculate that chances are this is going to be an add instruction. Chances are. So how about I take the upper part of the register of the opcode and use it as a register name? And how about I take the next bit and read something? At the end of the clock cycle, I'm going to give you the values of those 2 potential register names, the actual values of those registers, and putting those 2 registers here. That's cycle 2. Now, because we did assume that this is an add, next clock cycle, that action proved to be a nice thing to have done. So we're going to take the values from here, and we're going to say, okay, pass the first one to the ALU as the first operand, pass the second one as the second operand to the ALU, and do an add here. At the end of the clock cycle, write the result here, and then write it there. Okay. Yes?
By IR6 to 7 and IR5 to 4, are those like
Bits. There are bits. This is an 8-bit register that contains the instruction. For adds, because we're doing adds now, the upper 4 bits are 2 register names. Okay? Fair enough? Now, this was cycle 3. Cycle 4, we're going to take the result from ALU out. We're going to send it to the register file as one input. We're going to take, again, this through here and send it as a register name for the write port. And we're going to say RF write. Does that make sense? Okay. Now, I want to draw your attention to one. There's something I did wrong. No, I got confused. Cycle out, update 0. Sorry, this is a previous implementation where I forget the cycle. Okay. Forget the labels on top. Okay. Let's do this again. Cycle 1, I'm doing this. According to what I showed you before, okay, yeah, sorry, now I remember. So I've done that, cycle 1. Cycle 2, I do decode. Then I read the register file. In cycle 3, I read the, I messed up, sorry for this. I should have remembered this thing. I did decode over here. Then in cycle 3, I read the registers to make sure, but I could have done that earlier. I showed you that before. Now, what I saw here is cycle 4. I could have, this is embarrassing. Sorry for this. Okay. Okay. Let's do this again. Sorry, very quickly. And I'll explain what's going on. And it's a way to show you what else we need to do. So first clock cycle, let's read the PC and send it as an instruction. So far, so good. And we'll load into IR. That's cycle number 1 according to what I'm showing over here. This is not going to be an optimized implementation. Cycle 2, decode. Let's not read the registers yet. So we're looking at this and the control is deciding what to do. Cycle 3, now we're sure this is an add. Okay, we're going here, we're going to read this and read that. Fair enough? Again, this is not as optimized as I said before. Cycle 4 now. We're taking the values from R1, from R2. We're saying an add, load to LU, and update 0 negative flags. So far, so good. Cycle 5, we're taking this guy here and send it to the register file to write it, and the name from here. And we say register file write. Good. Cycle 6 now, we can take the PC. We can take the value 1. Notice that this is another input to the second operand over here. We can go to the same ALU, right? And we can say PC equals PC plus 1. Okay. Notice that this has taken 6 cycles, right? The difference here is the following now. In the first close cycle before, we're just taking this value here and reading the IR. Okay. Instead, as I showed you in the first table, what we could do in parallel, we can also do this. We can send it to the LU because the LU is still there. We can pass 1 over here and do plus 1 and send the result back. So now we're doing both fetch the instruction and PC plus 1, which fits to the table I showed you before. So this is an optimization, and I should have described it like that. Am I making sense? So before I showed you the instruction taking 6 cycles, where the PC plus 1 was the very last step. And now I'm going back to the optimization, which unfortunately I described early on. And I said, instead of doing this in the very last cycle, we can do it in the very first cycle. Done. Second thing, what I did before, I wasn't doing speculation for round 1 or 2. I was waiting for these things to happen to make sure that I have to read it. I showed you early on that I can read it before as well. Okay. Sorry for confusing you like this. I hope this makes it clear now. Subtract is identical. The only thing that's different is that in the cycle where we do the LU operation, we are going to do a subtract. Okay. So let me do this again with you as review. Feel free to doze off if you need to. Okay. And I'm not looking at you. I just happen to be looking at you. No comment. It wasn't meant to be personal in any particular way. In the beginning of time, there was nothing. You took the PC, you sent it to the memory, and you loaded the IR. In parallel now, the other thing you did is You went and you took the PC. You send it to the ALU. You put 1 over here. You said plus and load the PC plus 1. This is cycle 1. Now let's go to cycle 2. Cycle 2. We're going to speculate. We're going to say it's going to be useful maybe to read the registers. So while we're decoding, we're going to pass this as a register name and that as a register name, and we're going to get 2 registers. That's cycle 2. Cycle 3. color, magenta. Magenta looks nice. Cycle 3. We take these guys now, pass them as operands to the LU. We're doing subtract because this is what we want. And at the end of cycle 3, we update this guy and this. This is cycle 3. Finally, in cycle 4, we're going to send the results back to the register file. We're going to take the result from here and pass it as input to the register file here, and the name from the instruction. Notice that the error remains stable after cycle 2 onwards, and we're going to write there. Make sense? Okay. None is identical. Let's do ORI now and understand what's going on with ORI and why ORI is going to make our life miserable. Yes?
What's the optimization in doing the PC plus 1 in the beginning? Like,
It's something we got to do because we had the foresight to design the instruction set so that all instructions do this and maybe some more. We can do it early on, cycle 1, rather than wait and make it happen at the end. If the branches did not have the PC plus 1 component, it wouldn't be possible to do this in the beginning with no cost. It would be because you can always subtract 1 and go back and fix it, but that will have more cost. But because we designed the instruction set so that part of the calculation of the next PC is always the subcomponent PC plus 1, we can do it early on in the beginning and never have to take it back. So
you're also doing it in parallel, right? Like
Yeah.
at the same time you add to the PC, you're also reading from memory.
Exactly. And one of the key tricks to try to get as much performance as possible out of the designs is to use parallelism or concurrency. Do as many things as you can in parallel. Sometimes you're going to be certain what you do is a good thing. First cycle, PC and fetch from memory. You know you need both, period. Sometimes what you do is not going to be necessarily useful. Second cycle, you're looking at the instruction, got to do that, there's no way around it. And how about we read 2 races just because this may be useful? In the first case, this is not speculation, cycle 1. You're doing useful things no matter what. Second case, you're using concurrency, but it not be useful, it's speculation. Fair enough? Okay. Let's look at ORI now, and let's understand how decisions at the instruction level design can actually impact our machine underneath. Okay? So ORI, I hope you remember, for the first 2 cycles, things are going to be identical because they have to. First cycle, we take the PC, we go to memory, we get IR. We also go to the LU, we do an add with 1, and we get the next PC. Fair enough? Second cycle now, we go and we do, how about we read these 2 registers just in case they're useful. Okay, third cycle, the control does this and it says, okay, these were not useful. Why? Because I need to read K1, not this. So let's go back. 1 extra cycle now to do the right thing. So third cycle, we're going to go and we're going to say, how about you take 1, come on. Okay, can you see this? And load a new register here, value. That's cycle 3. Cycle 4, we're going to take immediate 5 as the second operand to the LU. This R1 we read here as the other operand, and we're going to produce the result here and update the flags. We're now at cycle 4. And at the end is cycle 5. We're going to go in and say, okay, we're very happy with what we've done. Let's take this value here, send it to the register file. Let's use 1 as the name. These are marvelous drawings. And let's write to the register file. Fair enough? This is going to be the longest instruction in terms of cycles. Why? Because the speculation we're doing at the second step doesn't pan out. Okay? Could you make this take 4 cycles? It's a trick question. In cycle 2, you have a choice. You can speculate that the most useful thing to do is to take the upper 4 bits from the instruction opcode and use that as names. Or you can say, how about I read K1? Because I think that's the most important thing. If ORI was the one designing the machine, that's what it would do. Right? I want to be faster. In that case, ORI will take 4 cycles because the speculation you did in cycle 2 turned out to be the right thing. Add, NaN, subtract, potentially shift will take more cycles because you haven't read the right registers. Fair enough? So you can play the statistics. The way to decide what's best is to take a lot of programs that people use, look at how often they use ORI, how often they use add, and if for whatever reason it turns out that ORI is more frequent than the other instructions, you do that. It's unlikely, but I'm just saying, that's the way you decide up front whether you should speculate one or the other. Yes, please.
What's the K you were like?
K?
Yeah.
My registers.
Oh.
Why they're called K?
Okay. Yeah.
Why not? I mean, they could be called L's, M's, M&M's. Okay, good. Where are we? How much time we have left? Load. Can we do load? Can I spare you the cycle 1, cycle 2? So we're in cycle 2 now, and we read R1 and R2. Okay. Good thing, because now in cycle 3, R2 is useful. R1 is useless for us because this is a load. But in cycle 3, we can go and say, take R2, go through this wire. You see this wonderful wire over here? Go through this multiplexer here and go to the address. Do a memory read, and at the end of the clock cycle, go to the memory data register and write the data from memory into that.
What's the memory data?
It's a temporary staging register where you put the data you got out of memory so that in the next clock cycle you can write to the register file. It's similar in function to the LU out. You have some big piece of logic that's going to take maybe a full clock cycle to produce something. You stage your result here so that next clock cycle you can write back to the register file. Underlying all of this is the assumption that roughly the amount of time it takes you to read something from the register file and the amount of time it takes you to read something from the LU or memory is significant that it kind of constrains the clock cycle. So what I'm trying to say here is the following. You could have said in one clock cycle, calculate a new result from the LU out and directly write it back to the register file. But underlying here is the assumption that I will make your clock cycle almost twice as long. And this is a fair assumption for most circuits out there. How do I know that? I mean, you have to design the circuit to see what it is, but take my word for it, this is usually what happens. Okay, so memory data register is a staging register that you use because this block takes quite a bit of time. So kind of, if you want to go directly into the register file, it will make your clock cycle twice as big. Fair enough? So that was cycle 3, right? End of cycle 3. Cycle 4, we go and we write into the register file. So we take this guy through this wire over here. We're sending to the memory data port for writes. We're using the R1 name, using the upper part of that multiplexer as the name, and we say RF write. That's load. Done. 4 cycles. Same thing as loads, so add, subtracts, NaN, shifts. Stores are even faster than that. Let's say we're in cycle 3 now, beginning of cycle 3, and we read these 2 registers. Both of them are useful for stores because one is address, the other is data. Again, address goes this way into memory. Data goes this way, and you say memory write. Done. And you're just talking to memory, you can do this in 1 clock cycle. That's store. Fair enough? Okay. Almost done. After this day, believe it or not, mark my words, you can build any CPU out there. Doesn't mean it's going to be the best CPU implementation, but you can build anything with this style. So let's do branch 0. Branch 0 says, if the 0 flag is true, then change the PC to be PC plus 1 plus the sign extended immediate 4. This guy. Okay. So first clock cycle, you take the PC, you go to the memory, you do a memory read, and you load into IR. You also do PC plus 1, first clock cycle. Fair enough? Second clock cycle, you look at the instruction. You cannot take action yet. So you naively go and you read 2 registers, just hoping that this is going to be useful. Third clock cycle, now you know this is a branch. If necessary, then you take the PC again. You send it as the first operand to the LU, and then you take the immediate 4 as the second operand, you do a plus, and you update the PC again. The net effect is, because it became PC plus 1 first clock cycle, plus PC plus sign extended third cycle, you get the branch you want. If the branch is not taken, you don't even need to do this. You can potentially even terminate in cycle 2.
So when you compile the code, the compiler calculates the offset from that point in the program to where you want to go in the program, and then puts that number in the
This is a piece of hardware that says there's an instruction somewhere in memory that tells me what to do. Who put that instruction there? How much effort they had to do that? This machine doesn't care. Right now, we're the hardware designers. Whether you tell programmers, you know what, real people do this by hand, so you go put the right thing there or not. Or you say, how about you use a convenient tool like an assembler and a compiler do that? This thing doesn't care. All it sees is a bit part in memory, it just does what it says. If it's wrong, too bad. It will do what you told it to do. It has no understanding of what you wanted to do, just what you said.
What I was saying was basically that the immediate 4 is just the offset from the current instruction.
Exactly. PC plus 1 plus sign, that's the definition. PC plus 1 plus the immediate 4, sign extended. Okay. And it was defined that way so we can simply implement it like this. Yes, miss?
So that's why you're adding the 4 immediate?
Yes, because that's the definition of the instruction. Again, I think I have it in the previous or the next slide. The definition of the instruction is this. Notice, there is an if-else statement, right? If then else. If the condition is true, do this. Otherwise, do that. Notice that there's a common sub-expression, PC plus 1. Because we define it that way, we can do that common sub-expression early on in the instruction execution without even knowing whether that's useful or not, because it is useful for every single instruction. That's a given. Actually, what I said is wrong. We do know that doing PC plus 1 is useful. Every instruction needs to do that. And because we define branches this way, we can then just add to it. That's the idea behind it. It's part of the instruction definition. And that should explain why Neos does it the same way too. Yes, please.
There are a few instructions that only use 3 or 4 cycles. Does the CPU still take 5 cycles to go through the whole thing?
The quick answer is no.
Okay.
Could it? Of course it could. You can just keep dancing. Let me just wait for a couple of cycles.
Yeah.
Would that be a nice CPU to have? I don't know. But no.
It's easier to build, right? It's easier to build.
Yeah, actually, it's not. This is easier to build. Okay. You're done. The other one, you have to add the extra cycles just because.
Right.
The only reason I can think why you may want to do that is for obfuscation, so people cannot